So we'll start with Newton's law today. Newton's law today. And okay, so before going to Newton's laws, what I would like to do is a quick recap of the equations of motion. So equations of motion, as you know, what are these? These are essentially three equations which basically relate the displacement, the velocity and the acceleration as a function of time. So remember again, we have discussed this at the very beginning, that the basic purpose of mechanics is to do what? Is to find out, is to find out the position or the displacement as a function of time. Once you know the position as a function of time, you know the velocity, you know the acceleration. So let's do a quick recap of the equations of Okay, so the first one, the most infamous one, equals V naught plus
AD.
Right? So given the initial velocity V naught and the acceleration A, you can find out the velocity after a certain time, as simple as that. Okay, so this equation as itself, it does not involve displacement directly or the position directly, which the second equation does, which is
S
x or s
is equal to
equals
u plus half AD square
good. Okay.
V square.
So this would involve the displacement. So this directly tells you the displacement as a function of time, provided you know the initial velocity and the acceleration. Okay, and the final one is
V square is equal V naught square plus 2AX.
in this case x. So these again, remember, although I am not writing the vector arrow, V, A, X, these are all vectors. So, and it is also to be kept in mind that the third equation is nothing new actually. It can be derived from the first. All you have to do is to eliminate time from the first two equations to get the third. How is that done? So from this you get T equals V minus V
V
naught
naught by A.
divided by 8. Substitute this T in the second equation. You get, so the third equation is nothing new, but it directly connects the velocity with the displacement without involving time. That's what it is. Okay, so this we all kind of know, but when we actually talk about Newton's law or take up problems involving Newton's laws and momentum conservation, the impulse momentum theory, we'll frequently be using these equations. So I wanted to make sure that all of us, we see this again, refresh our minds. So quick examples of these would be the free fall motion, for example. So what happens in a typical free fall is you release a particle from rest from a certain height and find out what the resultant velocity is or the final velocity is at any point during its journey. So free fall is a very common example where you basically start with an initial velocity of 0, that is, you just drop a particle from, let's say, a certain height h onto the surface of the earth. So this is the earth's surface. So if I ask you, what is the final velocity here? What do you use? You directly use the third one. So it will tell you that v square equals v naught is just 0. So it's 2 The acceleration due to gravity is still g. Right? So it's g and so v is the square root of g. Now likewise, if you toss a particle out from here upwards, you start with some initial velocity v naught again. This obviously is non-zero velocity. You are tossing with some velocity, and you want to find out what maximum height it reaches. Likewise, you can use the same equation again. So v, when it reaches the maximum height, then what is this velocity?
Zero.
Zero, right? So zero would be equal to
V naught square.
v naught square minus 2gh naught. Why is it a minus? Because
Opposite.
opposite, right? So basically your h is v naught square. Again, basic elementary stuff which we all have learned from high school as to how to use the equations of motion. Very, very simple equations. Very, very simple applications. Now, these equations can also be obtained, the same thing can also be obtained via the conservation of energy. Because remember, all we are doing, the framework in which we are doing the kinematics here is without air resistance. There is no friction due to air. That means that the final or the initial energy, the sum total of the kinetic and the potential energy is conserved. Because there is no dissipation due to friction from the air. So in this case, in the first case, the initial energy is just potential. So if you drop a particle from a certain height, what is its mechanical energy, total mechanical energy? Because it's dropped from rest, there is no velocity, so there is no kinetic energy. So the total energy EI would just be mg times h, the potential, the gravitational potential. And the final one, once it reaches here, the h reduces to 0. So it's entirely kinetic. So it's half mv squared. So as I said, these two would be equal because you do not have any dissipation due to friction. So EI equals En. That gives you V equals the square root of V. See, it's just the same. Right? So equations obtained from the results obtained from the equations of motion and from the conservation of energy just equivalent. There are two approaches to the same problem. Likewise, we do the maximum height calculation accordingly. The entire energy here is half mv naught squared, kinetic. It totally gets converted to mgh at the maximum. Again, you get v naught squared. But all this is in 1D. Because effectively, the entire motion is taking place along, if you like, the vertical y-axis. It's either up the axis or down the axis. But equations of motion are, in general, it can be applied to any dimensions, 2D and 3D. And the most popular one in 2D is the projectile motion. Remember the projectile motion where you actually project a particle at an angle with respect to the surface of the earth. So again, I won't be going through those, but what I would like you to do is just to, because as you understand, we are not here to kind of cover everything that you have done in 11 and 12, but rather kind of advance to more application oriented problems. But what this quick recap would do is kind of refresh your memories, and when you want to apply Newton's laws or these momentum conservation equations, or later the angular momentum and all these things, these equations will keep coming on and on. These are like the basic. So you want to be completely at ease with the application of these equations. So that's why it's always helpful if you go back and read a couple of chapters on projectile motion and equations of motion. So what happens in a projectile motion again? You project a particle at an angle theta, let's say, with respect to the Earth's surface. It's all a quick recap of the results. And you project it with a certain velocity v naught, right? And what is the resultant trajectory? It's a parabola, right? This is parabola. So it does a parabolic motion and comes back again to a certain point. And that point, starting from the initial point, is something called
Range.
the range, right? And through these equations of motion, now applied along the x, that is, along this direction, and along the y, you can individually apply the equations of motion along x and along y to calculate the range and also to calculate the maximum height the projectile can achieve. This is h max. All these results, if I tell you, immediately strike you. So the range is what? V naught square sine 12. Or is it sine 12? Sine 12. Over 2. The maximum height is V naught
Sine square
V
theta
naught
by
square sine square alpha
by 2g.
by 2. Right. Okay, so all these results you can derive from the equations of motion. But remember a crucial difference from the free fall case or from this particle projected in 1D along a single direction is what? See, when it reaches the maximum height here, the velocity is 0. But for the projectile motion in 2D, at the maximum height, the velocity is not 0. Why is it not 0? Did you get the question? So at the maximum height, in the 1D case, when you projected it straight up, it was instantaneously 0. But here, at the maximum height, it's non-zero, the velocity. How much is it? Vx. And what is Vx? V naught cosine theta, exactly. So here, it's still maintaining its horizontal velocity of V naught cosine theta. Because initially it was V naught cosine theta and vertical component was V naught sine theta. But since gravity is only pointing towards the y direction, the x component does not change. It is unaffected. So it continues with the velocity of V naught cosine theta throughout. What happens at the maximum height is that Vy, the y component of the velocity, becomes 0. But it still continues. Otherwise, it would have just dropped here. I mean, once it reaches here, it would have, if all the components vanished, then the particle would have just dropped out without continuing further. But that doesn't happen because the V naught cosine theta component continues. Obviously, because there is no gravity or any other force acting along the x-axis. Okay, so so what I suggest is you go back and have a quick refresh of the results for the projectile motion, and also maybe take up some examples from equations of motion and try to solve those on your own. Because these will be what we'll be frequently using when we apply the systems or any problem in mechanics and so on. Okay, any questions on this? Standard stuff, but still. Okay, so with this, let me move on to Newton's laws, and this I'll do via some slides today. Mostly discussing Newton's laws and the conservation of momentum and the impulse momentum theorem. But I'll do that via slides and take up problems, actual problems from tomorrow. So we should have the projector working. Can someone turn on the power as well? Let me phones. Yeah. Sure. Okay. Good. So let me erase this. Is it visible? Okay, so maybe we can start from here. So Newton's law. So the first law is essentially that there has to be something external, there needs to be an external agent which will actually bring a body from its state of rest to motion, and also vice versa. That external entity is something called force. So the first law, also known as the law of inertia, is basically a qualitative definition of force. You can remember it this way. The first law gives you the definition of force. So all Newton's three laws basically talk of the nature and the quantification of this entity called force. So remember from the very first lecture that we had, or discussion that we had, all these fundamental forces. So force is something that you need to have in order to bring something to rest or to motion. So that force, the nature of the force, how do you define the force, is something that Newton, for the first time, he kind of classified and quantified. So the first law, also known as the law of inertia, gives you the definition of a force. That force is something, that external something that you need to do to a body to bring it to motion if it's already in a state of rest, or to stop its motion. What did I say before? Sorry. To bring it to motion if it's already at rest, and to stop it if it's already in motion. Sorry. Okay. Yeah. And the second law, which as in itself, this is not the exact law, but the law is that the force is the rate of change of momentum. Okay, so let me just emphasize that again, because this is a crucial point that people often miss. Force equals mass times acceleration is true, but it's true if the mass is constant. So force is basically the rate of change of momentum. So this is the second law. Now, what is the momentum? How is the momentum defined? Mass times velocity, right? So it's d dt of m times v. Now, only if m is constant, the mass is constant, then only you can pull this outside the differential. If it's a function of time, if the mass is such that it's a function of time, then you cannot pull it outside the differential. As it happens for rocket propulsion. The fuel actually burns, and hence the total mass of the rocket is actually decreasing as a function of time. So provided you have mass constant, then you write m dv dt, and dv dt is nothing but the acceleration. So then this is true. So this we popularly write as Newton's second law, but this is the origin. To be precise and correct, force is the rate of change of momentum, and not just mass times acceleration. Okay. Anyways, so what it does is it quantifies the force. The first law gave you a definition of the force, but that was qualitative. No quantitativeness was there to it in the first law. But now it tells you how much the force is. If you give me the momentum, that is the mass and the velocity of the particle, I can tell you the force. That's how I do it. So the second law quantifies the force. And the third law, reaction-reaction pair, what does it say? In words it says that every action force will have an opposite reaction force which
Acting on different
will have the same magnitude but in direction would be opposite. The thing to keep in mind here
They
again
act on
is they do not act on the
bodies.
same body. If that would have been the case, then nothing in this universe would have moved. If they acted on the same body, then they would have cancelled all this. So the thing is, if you have something, let's say this laptop resting on the table, the laptop is actually working or exerting a force equal to mass times gravity onto the tabletop surface. The tabletop surface as a reaction force is generating this normal reaction N of the same magnitude onto the laptop. Okay. So these action-reaction pairs, they act on they are equal and opposite, that's true, but they do not act on the same body. So that was the point. So basically no force in nature can exist alone. There has to be an opposite reaction force. If you generate a force, there has to be something which is a reactionary force. So forces always operate here. So essentially the third law gives you the effect of the force. What the force might be. So the first law, again, qualitative definition of the force. Second law, quantification of the force. And the third law, effect of the force. The universal law of gravitation, as you all know, this popularly doesn't fall into the three categories of Newton's laws of motion. But this is Newton's another contribution where he actually quantified the force of gravity as well. How much would that be? We have two masses m and m prime separated by a distance r, then the force of gravity, which is always attractive, as opposed to or in contrast to electrostatics, where it might be repulsive. Although the form of the force is very similar. Remember Coulomb's law? It's K1 Q2 over r square. So it's again a inverse square law there as well. Again the product of, rather than product of masses, product of charges.
with
But
sign.
Electrostatics, the force might be repulsive or attractive depending on the kind of charge. But gravitational force is always attractive. Okay. Further slides on Newton's laws. And this basically giving you the law in terms of words. The crucial thing here is the third one tells you that F12 is the inverse minus, you see, 1, 2 has become 2, 1, telling you that these two forces are equal and opposite. The minus sign is for opposite, and if you take the magnitude on both sides, the magnitude is the same. Okay, so again, it's pretty much the same thing. For every action, there is an equal and opposite reaction, all these standard things. Now this slide is rather, in a single slide, you get to see that in order to provide a net force to something which is already at rest, in this case, the rocket, you need to exert a force. So that's the first thing. That comes from Newton's first law. If you do not do something external to a rocket already at rest, you do not move the rocket. So net force has to be provided. But the net force has to overcome, if you are to kind of launch the rocket from the surface, it has to overcome its own weight. That's why you need an upward thrust. What will this thrust do? This thrust will basically counteract the weight of the rocket such that it moves up. And how is this done? This is essentially done by burning this fuel. Have you ever seen videos of rocket launching?
Yes, sir.
From the popular NASA videos or the Kennedy Space Center. So there you might have seen a huge amount of smoke surrounding the rocket. It's almost like the rocket would become invisible. Right? It's surrounded by a huge amount of smoke. What did they actually try to do? They're actually burning the fuel so much with such high pressure that this thrust is like the reaction force. The more you force on the ground due to the burning fuel, the more would be this reactionary force. So this thrust will increase. And it has to be that large such that it achieves this thing called the escape velocity. What is the escape velocity?
The minimum velocity required to escape from its gravitational field.
Exactly, right. The escape velocity is something that you need to give to a particle. Might be a rocket or might be a tiny particle to escape the gravity field of the Earth. And if you go back to your lessons on gravitation, you will see that this escape velocity is independent of mass. It does not involve mass. Was that square root of gr or 2gr, I forget? Gr. 2gr. Right. So this expression does not involve the mass of that particular object that you are launching. Okay. And that's why it comes out to be this number 11.2 kilometers per second. So it has to at least achieve that amount to escape the gravity field. Okay. Okay. So the basic idea is this launching of the rocket is a very illuminating example where the first law automatically comes into picture because you have to bring it to a state of motion from a state of rest. First one. How much force is needed is given by the second law. And the effect of that is this thrust, which is given by the third. Okay. This is a cartoon slide summarizing the three laws. So this guy asks Jimmy, what is Newton's first law? And he says, what is in motion remain in motion, and what is at rest stay in bed unless their mothers call them to get up. This happens to you? Huh? Not now, maybe. Or maybe still.
Yes.
How many of you are hostelers here? Okay, most of you. Okay. For you, it's what? The security guards call? Oh, I don't know. Who wakes you up? Is it the alarm clock? Okay. But for the day scholars, maybe. Is it still your mother?
Yes, sir.
Yeah. So it's still there. Yeah. How many times do you actually snooze your alarm?
5.
I mean, I do it as well. I've reduced it. Over the years, I've reduced it. But I still prefer to sleep 5 minutes more. Okay. So Newton's laws. So that's what I wanted to talk about in general. Discuss about Newton's law. Any questions till now? No? Good. Okay. So Newton's laws, the second law, as we saw, involves something called momentum. It's the rate of change of momentum. What is this momentum? How is it defined? It's basically the product of mass times the velocity. And crucially, it's a vector. Remember, whenever you multiply or do a product with a vector with a scalar, the resultant is again a vector. We're just multiplying the vector v, the velocity vector in this case, with a scalar quantity which is the mass. The resultant is again a vector. So these things are crucial to keep in mind. Quantities that you're talking about, are they vectors, are they scalars? Because physical quantities are of both nature. Right? So you must kind of be clear as to what the nature of that quantity is. So momentum is mass times velocity and is a vector. And how is momentum calculated? Well, these are some very trivial quantitative examples. If you have a momentum, a mass of something like mass of the wagon here, let's say, is 30 kilograms, moving at a speed of 2 meters per second, then it's as simple as 30 times 2. So make sure you understand how the units are taken into account as well. Mass times velocity, kilograms, meters per second. That would be the unit for momentum. But this is very crucial. People often miss out on units. So you shouldn't do that. You should understand as to what the units are. And many a times you will require a conversion of units. Some quantities would be given in standard SI units. Let's say the momentum here, the mass here is given in grams or kilograms, and the velocity in fact is given in centimeters per second. Then you cannot write the momentum in kilograms centimeters per second, but it's customary to write it in standard form. So you convert the centimeter per second to meter per second, as the case may be. We usually prefer SI units, the kilogram, meter, second, standard form of. So look, when you do problems, please look into the units used. Like for example, we're talking of the diffraction grating in the lab there, today morning. So the diffraction gratings are actually given in per inch, the number of lines per inch for people in group 5 especially, and later for all of you. It's given in per inch, so you need to convert that to appropriate units. Okay, so you need to take care of these things as to in what units it's being mentioned. Okay, and the momentum can be increased or decreased depending upon both the mass and the velocity. You might have a huge mass and a low velocity, or have a low mass and an increased velocity to give you the same momentum, because it's a product of the two. Okay, so that's basically the summary of this slide. Is linear momentum or simple momentum is a product of mass and velocity of an object. Like velocity, linear momentum is a vector possessing a direction as well as an angle. This is how it's defined, and these are the units. Okay, so as I said, even a small object can have a large momentum. Just like the bullet, it has hardly a few grams. It's in mass, right? But the momentum is high because the velocity with which it's triggered, that's very high. So either you can manipulate the mass or the velocity to achieve a particular value. That's the idea. So likewise, the glass can have a large momentum even if it's moving very slow, because it has a large mass. Okay, this is again an example on conservation of momentum, but maybe I'll skip this slide and directly go on to this one. I think this one is more illuminating. So basically, I'm already moving on to, after discussing Newton's laws and the concept of momentum, already moving on to something